Morning. Well, thank you, Jim and Miles, for the invitation to speak. I was delighted to accept the invitation to talk on a topic of which there is almost no material. But I guess this is the point of the meeting, is to galvanise our thoughts. And when I started thinking about it, actually there is quite a bit to say about this, but I took the liberty of slightly altering my title. Instead of being Regional Impacts of 1.5 degrees C, I'm going to speak on regional impacts at 1.5 degrees C, because it's not just warming that's happening, there's other things going on in the climate system, as you'll see. And actually, my first slide does cover the last question, actually, of when we may see the first year at 1.5 degrees C. We should be careful to distinguish between the first year at 1.5 and long-term 1.5. But this is a figure from my Met Office colleague, Doug Smith, who does the decadal forecasting. The green plume is the CMIP5 RCP 8.5 multi-model ensemble, so all the IPCC climate models. The black curve is the observed annual temperatures. The red plume is the verification of the decadal forecast, and the blue plume is the Met Office decadal forecast, well, actually a 5-year forecast, issued in January this year. So it's initialised from current observations and tries to account for natural variability as well as long-term climate change. And you can see basically that forecast is expecting that after the sort of the recent hiatus, we're expecting the global temperatures to be fairly well within, or perhaps even at the upper end for some years of the CMIP5 projections. So an important point though is that the changes here are relative to a present-day baseline, but of course we're interested in changes relative to pre-industrial. And as Valerie was pointing out, I think it was her first slide, we're already at 1 degree. We had the first year at 1 degree above pre-industrial last year in 2015. When might we see the first year at 1.5? Well, bearing in mind it might be an individual year, not the long-term change, the green plume accounts for the year-to-year variability and uncertainties in the climate response. But it's possible, according to this, that we may see the first year at 1.5 in about a decade's time, possibly. It probably will be later, but it may be as early as a decade. So that's quite interesting to think, because these thresholds of round numbers, 1 degree, 2 degree, 400 ppm and so on, they're quite iconic, and they, even if they don't mean anything particularly physical, they kind of capture the imagination. And I think we're certain to see newspaper headlines as soon as we have an annual mean global temperature at 1.5 degrees C above pre-industrial. But how should we react to this? There could be two extremes of reaction, and I'd caution against both of them. First of all, we should not panic. I can just imagine some of the headlines saying that at 1.5 degrees, the world's going to end. No, it won't. But equally, I don't think we should be complacent either. It will be easy to look at what's happening around the world in the first year at 1.5 and think this is an indication of long-term change at 1.5, and that won't be the case either. Many more things will play out over decades and a century and so on when the average is at 1.5. So within these two extremes, there's lots to think about and lots to take seriously. So as I say, we're looking more at the longer term changes. And I was looking around at what information there is relevant to the issue of 1.5 degrees and 2 degrees and comparing the two. As I mentioned, there's rather little at the moment explicitly looking at this question. That which has been looking at taking existing IPCC projections and say looking at a time slice within, say, the RCP 8.5, the high emissions scenario. So there's one paper which I'll mention shortly which does this. So it basically looks at the red plume is the high emissions scenario, RCP 8.5, and you can look at the 20 or so years, or maybe 30 years around the time of passing 1.5 relative to pre-industrial. So this is adding on. So the present day baseline in this figure is about 0.6 degrees warmer than the pre-industrial baseline, so that's why the dotted lines are slightly lower. And then you can look at the 20 and 30 year average, again at 2 degrees, for example, and compare the two. But there's very little information even taking that simplistic approach. So what I've also done in this talk is look at what we know about impacts projections for RCP 2.6. As Valerie said, that encompasses 1.5 degrees, although it's not really designed to be a scenario of staying below 1.5. But the multi-model mean gives you some idea of approximately 1.5. It's something to go on. And then similarly for a 2-degree scenario, you can look within some of the results of RCP 4.5. That's a bit more than 2 degrees in actual fact. But some of the points I'll make will I think, still stand based on these two projections. So first of all, one of the most obviously sensitive parts of the climate system in terms of regional impacts are glaciers. So glaciers are already retreating. We're familiar with these kind of before and after pictures of glaciers having disappeared from where they were a century or so ago. And the panels on the right-hand side show from the IPCC AR5 report for different glacial regions. We're showing, in terms of observations and also model reconstructions, it's clear that glaciers are retreating in all regions of the world. So if we look at what that means going forward, this was a paper published 4 years ago which looked at the changing glacier mass balance in all these regions, expressed in terms of sea level equivalent on the left-hand side and the percentage glacier volume remaining on the right-hand side. And this figure is for Central Europe, and it's looking at the RCP 2.6 scenario, RCP 4.5, and RCP 6.0 and 8.5. So all the emission scenarios, several different realisations for different models, and also the thick coloured line shows the multi-model mean. So using the climate projections to drive a glacier mass balance calculation, basically. And of particular interest here is, of course, RCP 2.6, which I'm using as a proxy for the 1.5 degree scenario. That's the thin red lines, which is nearer the bottom. But you can see that even in that extremely low scenario compared to the rest, the glaciers in Central Europe, so the Alps, are projected to continue to decline, perhaps losing 50% or more of their mass by the end of the century. And the higher scenarios even more. So the RCP 4.5 perhaps up to only 20% of the glacier volume remaining in the multi-model average there. And that picture is seen in all the glacial regions of the world. So we've got Alaska, Greenland, Russia, Scandinavia, Svalbard here. So again, you get the same picture. All the glaciers are projected to continue to lose their volume, perhaps sort of 20 up to 30% under the low emissions, under the 1.5 scenario. And there's another, just to complete the set, here's the other glacier regions here. So the same pictures. So everywhere in the world we're expecting to continue to lose glacier mass. And as someone who enjoys the mountains, personally I find that quite sad. But also more importantly, this is the reason for this extreme ambition under the Paris Agreement is that we're committed to the loss of land ice and therefore sea level rise, and this is why the small island and low-lying states in particular are keen to avoid this, because this change is already locked into the system to some extent, even at low emission scenarios. Also, thinking about the cryosphere, changes in permafrost. This is a figure from our chapter in IPCC AR5 in the Working Group 2 Terrestrial Ecosystems chapter, looking at the CMIP 5 climate model projections of changes in permafrost extent. So RCP 2.6, the 1.5 degree scenario at the top, and then RCP 4.5 at the bottom there. Each line is an individual system model, and it's showing what they're projecting for the changes in permafrost extent. You'll see they disagree quite a lot on the present day state, but that's the nature of these models. They are quite uncertain. But they are showing a common trajectory of a downward trajectory of permafrost extent, even under the 1.5 degree scenario, although it does seem to stabilise and flatten out by the end of the century. So we seem to be losing some permafrost, but not all, under 1.5 degrees. But then under the approximate 2 degree scenario, RCP 4.5, we see a further decline in permafrost extent, which doesn't necessarily stabilise by the end of the century and perhaps continues. As for the water cycle, changes in land hydrology, this is from the one paper which is explicitly looked at 1.5 and 2 degrees, Schlusner et al., which was very heroically put out very quickly last year. So these used used an existing set of impacts projections from the study called ISIMIP, the Intersectoral Impacts Model Intercomparison Project, which used existing IPCC projections to drive a set of hydrology models. And they took these time slices at 2 degrees and 1.5 degrees within the RCP 8.5 scenario. You can see there's a complex pattern of change at both levels of warming, some areas getting wetter, particularly in the high northern latitudes, some areas getting drier, such as in Europe, South America stands out. The pattern of change is similar at both levels of warming, and in fact there's some areas where, although there's some areas where there's no clear signal, the models disagree on the sign of the change. That's in the grey hatched areas. But you can see there is some discernible difference between the two. The wetter areas get even wetter by 2 degrees and the drier areas are even drier by 2 degrees. So we can ameliorate some of these changes if we can stay at 1.5 degrees. I'm not aware of anything translating this into water resources and flood risk as yet. This is work I think which should be done and actually is underway. I'll just very briefly talk about biodiversity, because I know Pete Smith's going to talk more about this later on. The key point I wanted to make here, again this is a figure from IPCC AR5, is it's not so much the magnitude of change, but often it's the rate of change which is a concern. So on the bottom right, that panel is showing an assessment of how different groups of species may adapt to climate change by migration or dispersal, in terms of how they can move across, how fast they can move across the landscape. On the top left, this is again the RCP projections, the climate model projections for the coming century, compared with observed changes, but in terms of rate of change, rate of global warming as opposed to magnitude of warming. And then the top right kind of translates one into the other in terms of this concept of what you might call climate velocity. Imagine a particular envelope of climate space moving across the landscape, mostly poleward, as the climate warms. And to cut a long story short, the main point is that the rate of warming at the higher emission scenarios could be too fast for many species to keep up with, particularly plant species, which can't physically move. They can only disperse through dispersing seeds and so on. But the lower rates of warming, especially the RCP 2.6 scenario, could be well within the ability of species to adapt through migration and dispersal. So we could be avoiding many of the major impacts on the biosphere in that way. However, it should be pointed out that we're already seeing changes in phenology, the timing of seasonal events, so the arrival of migratory birds, bud burst, leaf out, insect emergence, that kind of thing. So this is a meta-analysis of different changes in phenology, the rate at which these phenological events in spring are coming earlier in the year. And the key point is different groups of species are showing these phenological responses at different rates. So even if things are adapting by changing their phenology, we may be disrupting ecosystems because these rates of change are happening differently for different species. So we're already changing ecosystems. So again, this needs to be looked at, I think, in the particular context of 1.5 degrees and the speed at which we get there compared to 2 degrees. And also in relation to ecosystems, and this is what I wanted to say, it's not just about impacts of warming, there's other things happening as well. As we're well aware, avoiding 2 degrees C may involve use of the land for things like bioenergy, carbon capture and storage, carbon sink plantations and so on. The land cover scenarios that go into the emissions scenarios do make assumptions about change in land cover. At the top, this is a map of the percentage cover of primary vegetation at the present day. So red is almost 100% primary vegetation. The other colours are not primary, so disturbed land which has already been affected by humans, and dark blue is the most disturbed area. The key point I wanted to make was in RCP 2.6, so the highly ambitious aggressive mitigation scenario involves a lot of land use because it includes a lot of bioenergy. So I think this is something which will probably come up tomorrow, I think. So we need to consider not only impacts of climate change itself, but the impacts of what we do to try and avoid it. I'll just finish by talking about the impacts of climate change on crop yields. This is showing crop yield changes against local temperature changes for the tropics on the right and the temperate regions on the left. For the lower levels of warming, it seems that temperate croplands may be able to, the yields may not decline so much or may even increase slightly, especially if adaptation is included. But that's not the case for the tropics. We do expect some declining yields in the tropics, even at lower levels of warming. But the key point is that we also need to account for the effect of CO2 fertilisation. Plants are obviously affected by CO2 directly, as well as it being a greenhouse gas. And this figure, I've zoomed in on one of the figures. If you look carefully, the dots are the studies which include CO2 fertilisation and the crosses are studies which don't. And you tend to get a greater increase in yield when you include the direct effect of CO2. And the point I wanted to finish on was that we don't know what the CO2 concentration will be at 1.5 degrees C. It depends on some quite uncertain issues such as the climate sensitivity and the mix of greenhouse gases. There's other greenhouse gases as well as CO2 which are increasing, such as methane, which don't have this effect on plants. So if we look at the 1.5 degree level in the bottom panel, we could see reach that fairly early, perhaps at a CO2 concentration of maybe rough estimate about 430 ppm if we have high climate sensitivity. But if climate sensitivity is low, or we have a greater mix of CO2 in the total greenhouse gas mix, then we could see it could be 550 ppm by the time we get to 1.5. So that could have a substantial impact on the actual impacts on crop yields and also ecosystems as well. And I'll just put my conclusions up to finish. Thank you.